So the context for this talk is collaborative applications. So if you imagine apps like Google Docs and Figma, they are quite common nowadays. And what they allow you to do is you can have multiple geo-distributed users who can all work on the same project at the same time. While these apps they are networked and so on, but essentially they are all centralized, right? In particular, I mean, they are centralized for a reason because you want to resolve conflicts. And if you happen to have network partitions where one of the users is not able to connect to the server, or multiple replicas of the server are not connected to each other, then the apps become unavailable, right? So I want to move to a world where these users who are disconnected may work on their own versions of the apps independently. And when the network connection gets back to normal, you want to take these different divergent versions and you want to merge them together, right? Resolving the conflicts. So how do we do this? We can take inspiration from distributed version control systems like Git. In Git, your project might have a main branch where you've sort of forked off a feature development branch where you're working, and you may have had bug fixes on the main branch. And eventually, when the feature is ready, you merge it back into the main branch. And this merge in Git goes through what is known as a three-way merge. So in a three-way merge, you have the two versions, but also the lowest common ancestor in the commit history. That gives you the causal context for the merge. And this merge can either succeed with the value, the new file, which is merged, or it may fail. Git will say, hey, you have conflicts. I don't know how to resolve these conflicts. It will present these conflicts to the user, and the user will have to manually resolve these conflicts. So mergeable replicated data types sort of take this idea and apply them to arbitrary data types rather than just text files, right? And the promise of mergeable replicated data types, MRDTs, is that you could take your own sequential data type, slap a three-way merge function on top, and what you would have is a replicated data type, right? That's the promise. So here is an example. So here is a replicated counter. And the counter has three operations: read, add, and multiply. I have an implementation here. It happens to be an OCaml, but that doesn't matter. The thing to notice is that each of these operations themselves are completely sequential, right? They are just what you would have in a purely functional setting. And they don't appeal to the distributed nature. And all of this is sort of encoded in this merge function. This merge function takes three arguments: the LCA, the lowest common ancestor value, and the two versions of the counter. So these are all integers in this particular case. And the merge is computed as the sum of the value of the counter at the LCA and the two deltas between the LCAs and the versions, right? To see how it works, you might start with the counter value as 7, and you increment on one branch, you get 8. You may multiply the counter by 3, you get 21. The net effect of doing these operations is that you've incremented the counter by 1 on the left branch and 14 on the other. And when you merge these two counters together, the merge will yield 22, which is the value of the counter at the lowest common ancestor, and the effect of doing operations on the two branches, right? So that's the idea, and you get 22 as a result. And the same thing happens on the other side as well, right? So these replicas converge, and the world is great, right? So the question that we wanted to ask in this work is, does this three-way merge idea generalize? It sort of does. So let's take another data structure. So this is a distributed version of a set, and it's called an observed removed set. And the idea here is that in a set, if you happen to have concurrent addition and removal of the same element, you have to do something, right? And OR set says that because the remove has not seen the concurrent observe, the add will win, right? The add will always be in that set. So the promise of MRDTs is that you could take these merge function, add it on top of a sequential data type. Let's take the merge function that was presented in the OOPSLA 2019 paper that introduced MRDTs, right? So you have a merge function which takes an LCA v1, v2 again, and the merge function returns you a new set, which is the union of the unmodified elements that are present in the three versions and any new elements that have been added in v1 and v2. So if you sort of squint, this is isomorphic to the counter merge that we had seen earlier, just lifted to sets, right? So the question is, does this preserve OR set property, the add wins property? As you would see, unfortunately, it doesn't. So let's say that the set is initially a singleton set with element 1. If you add 1 to it, because of the nature of how this is implemented, 1 is already there in the set. So the state of the set doesn't change. It would still be 1. You could remove the element 1 on a different branch. You get an empty set. If you just look at the execution at this point, there's a concurrent add and a remove. Right? Or add when set says, hey, there should be this 1 in the merged set. But unfortunately, this is not the case. The crux of the problem is that because of the fact that there was an add, but this add was essentially ignored. The state was not updated to capture the fact that there was an add. Things go wrong, right? But things go wrong in an interesting fashion. You do have convergence. Both of these different versions converge to the same empty set, but the intent of OR set, which is that add wins, is not preserved, right? So that's key. So how do we concretize intent? We need a specification language where we can talk about the properties that we want. Because we are in an eventually consistent setting, this needs to be rich enough to capture the constraints of complexities of eventual consistency. And the thing that we observe is that even simple data types attract enormous complexity when you make them distributed. I think this was succinctly captured by a tweet by Lindsay Cooper many years ago. I mean, it's just hard, right? If you want to talk about counters, they're just hard in a distributed setting. So in our mind, we decided that we need mechanization to connect specifications to implementations, right? And this is our work. So our work is called People. It's a framework for building certified MRDTs. And People is implemented as an F-star library. F-star is this proof-oriented, solver-aided programming language. So our specification language is event-based. And it's based on the work that was introduced in POPL 2014 called replicated data types. And what we do is we sort of take the replication-aware simulation relation that was introduced in that work and extend that to MRDTs in order to connect the specification and the implementation. And the thing that we observe is that in local-first software, you really want to optimize for local operations because local operations far outnumber remote operations. So in our work, what we focus on is implementing space and time-efficient implementations. And in particular, we have the first certified implementation of a replicated queue that has constant time push and pop operations and a linear time merge. So we also have this novel notion of composition of MRDTs and their proofs. And I'll talk about this a little bit towards the end. And the advantage of doing this in F-star is that you can extract OCaml code, which is compatible with this Git-like distributed database that we have in OCaml called Lerman. Right? So, okay, so that's the setup. So let's actually go and fix the OR set example that was broken. So the standard idea is to discriminate multiple additions by associating a unique ID. And let's do that. So here's a singleton set with an element A with a unique ID 1. And when you do an addition, you pick a new unique ID. It happens to be 2 here. And you add a new element to the set. Right? And now your remove has to do a little bit more. It has to look at all A's and remove all of them from the set. Here there is just a single A. It removes it and you get an empty set. The merge function just remains the same, right? We haven't changed the merge function. That remains the same. So when you merge, the common elements between the 3 versions is empty because on the right-hand side, you have an empty set. And the newly added element is A, 2. So that appears in the merged version. So this is what you want from an OR set. There was an add, and the add survives. So our MRDT implementations are plain, purely functional, standard implementations of sets. I mean, the only subtlety here is that for each of the operations, we assume that the operations get from the runtime a unique Lamport timestamp. And this Lamport timestamp is used for unique IDs in this example. And these Lamport timestamps can be locally generated. So there is no coordination required between replicas to do this. OK, so that's the implementation. So what's the specification language? Our specification language is Sort of very similar to what you would find in relaxed memory models. It's event-based, so you have a set of events, and you have functions for extracting operations, return values, and the timestamp. And you have a visibility relation, which is an irreflexive transitive relation between events, which sort of capture what events are visible to what other events. For example, on the right, you have an abstract state, which corresponds to the concrete execution that we saw in the previous slide. So you have these events, you have operations add and remove, and you have visibility relation between the events. And the question that specification has to sort of answer is, hey, given this abstract state, if I do a read here, what value should I see? And the specification for the OR set says that if you do a read, you get a set of all A's such that there exists an event whose operation is add, and there does not exist another event F, which is a remove of A, which happens to witness this add. So this is essentially capturing the add wins property. Right? Okay, so in this case, if you sort of look at this, I have an add at the top, which was witnessed by the remove, so that effect is gone. But the add on the right has not been seen by a remove as far as this read is concerned. So this read will return A, right? So that is what we want. So we have this specification and the implementation. Now we need to connect them. So we need a simulation relation. So for the OR set, the simulation relation is fairly simple. It says that if you happen to have the pair A, T in the concrete state, then it must be the case that there is an event E, which happens to be an operation add A at the timestamp T, right? And there does not exist another event F, which is a remove, which happens to witness the add. If you sort of squint at it, this is the same specification as what we had for the read. As your data structures, the implementations get complicated, the simulation relation also tends to get complicated. The main proof burden here is that you have to actually show that this relation is a simulation relation. So this is proof by induction on the execution trace. And we have to show this separately for operations and the merge function. Right? And using this technique, we've proved a number of MRDTs. So what I've highlighted is the OR set MRDT. And I present the verification time and the verification effort. So F star is solver aided, but you can also do extrinsic proofs. So the thing that we observed is that if you happen to add the extra lemmas, the verification time goes down much, goes down a lot, right? So there can be a lot of work to be done in this space. So we also have verified implementations of efficient versions of OR set, which doesn't have duplicates. And we have a version of OR set that also uses a balanced binary search tree in order to represent the set so that the local operations are fast. Okay, so in the rest of the time, what I want to do is to talk about composition. So Martin Kleppmann tweeted about a 10-line CRDT algorithm that he knew was correct. He assumed that it was right, and he taught it in a course, and he wanted to prove it right. So he spent hours and hours trying to prove it, and he found that it had a fatal bug. And the interesting thing with the bug is that it only occurs during the composition of two individually correct CRDTs, right? So these are correct, but when you put them together, this bug appears. So Martin Kleppmann, for those of you who don't know him, is an expert on CRDTs, right? If experts spend hours trying to prove 10-line algorithms right, then we must be doing something wrong. So we said, how do we improve the situation? So in people, we have a way of writing MRDTs in a way that they are composable by construction. So for this, what we do is we take this example of IRC-style chat. So users can send and receive messages on channels. We can represent the application state as an MRDT where the keys are strings and the values are mergeable logs. And the goal that we want to have is that you want to prove the correctness of the map separately from the correctness of the log. And you want to put them together. And with no additional effort or little additional effort, you want to prove that the application is right. So the implementation of this generic map is given here. There is a lot going on here. But the key idea here is that The map itself is parameterized on the values of the map are themselves MRDTs, and the merge function of the map appeals to the merge function of the underlying data type, right? And the simulation relation appeals to the simulation relation of the underlying data type. So I'm ignoring a lot of detail, but what is happening here is that you prove this map once and for all, right? And you can construct this app by taking your mergeable log, instantiating your generic map with that, and then you're done. Essentially, the proof of correctness of the chat application follows from the composition, right? The details are in the paper. I would encourage you to have a look. So yeah, so I'm almost done. So we have this library, which is a certified implementation of MRDTs in F-star. It's open source. You can play around with it. We have space and time efficient implementations. We focus on composition. So the library is sparse now, but we plan to expand it a lot later. The paper has formal description of the system, soundness proof, also written in F-star. We have a large case study on replicator queues and a lot of performance results. So do have a look. Thanks very much.
Hi, I was curious, what do you mean by having an implementation? I assume, in other words, what are the primitives that you need? In order to implement this, you need a lot of infrastructure.
So good question. So the distributed systems infrastructure is actually given by Ermin, right? The Ermin library, which is the distributed database on top of which we actually run this. So what we do in F-star is just the purely functional version with the merge, right? That's all we do in F-star. So it's all very simple, actually sequential verification in F-star, but the distributed systems aspects is all taken care of by the Ermin middleware.
The example that you gave of the composition was trivially correct and an obvious consequence of the composition itself. But the Kleppmann tweet is referring to a CRDT that didn't have that property. What's the additional verification effort or process for doing a composition like Kleppmann's where there's some interesting interaction?
So good question. So if you wanted to prove something more, this has to be part of the value type, right? So the simulation relation for the value type has to say something about what you want to prove, right? The additional MS has to be encoded in the simulation relation, and that sort of flows through because the simulation relation of the map refers to this particular simulation relation, and you can prove it. It's a little bit of I'm sort of hand waving a bit because we haven't done large proofs on this, but that is how I would organize that.
Sorry, but maybe take this offline because we have to go. So let's thank Casey again.